All right, well, good afternoon and welcome to the Scripps Technical Forum. I'm Douglas Alden and I'm the lead engineer with the Center for Western Weather and Water Extremes here at Scripps. In addition, I function as the STF chair and get assistance setting up and running STF for my colleagues here on campus, Gwyn Nero and Vanessa Scott. Gwyn is the Director of Corporate Affiliates, Business Development, Industry Outreach and Innovation, and Vanessa is an Industry Relations and Innovation Analyst. If you have missed any of our recent presentations, you can find them on the Scripps Technical Forum playlist on the Scripps Oceanography YouTube channel. You can get there from the Scripps Technical Forum website, stf.ucsd.edu. There's a list of all the past presentations and links to the recorded presentations. Please know that today's presentation is being recorded. You've all been muted when you logged into the conference, but if you have a question for one of the presenters, please use the Q&A function or just unmute. Today, we will have a presentation by Lawrence Younan, Senior Application Scientist with CHARACTERIZING on characterizing algal blooms using real-time fluorescence monitoring. So with that, I am going to hand it off to Lawrence.
Okay. Thank you all for having us talk to you about some developments that Turner Designs has been doing over the years with fluorometers, other instrumentation. So I'm going to start off by going over a small, if I can make my screen work, a small history of what Turner Designs has gone through. Those are the instruments that we kind of like an instrument timeline almost for Turner Designs. And as I was saying, those instruments on the left-hand side there may look familiar, like the 10EU, which was the workhorse of the old. There were protocols around looking at determining chlorophyll in vitro, like the APA method 445 was written solely around the 10EU, which are great instruments to have used in the past. They were robust, they last. That's actually to this day, we have people still using the 10EU as how well built they were. But they had issues, as did all old instrumentation, and I'll speak to that a little bit. In that they drift. So this idea of drift existed in these old instrumentation due to the changes in the lamps and the LED, the lamps and the filters, the polarizers, moving parts. They needed maintenance. It was pretty tough to control a 10EU. It was more like the 10EU was controlling you almost, because it had to be maintained over time. Whereas these days, the progression has been, let's move to, especially with the advancements in electronics, let's move to these smaller, easier, simpler to use instruments that don't require all that babying almost, right? So you'll see on the right-hand side there, we have that little single tube fluorometer, fits in the palm of your hand, integrates into almost any equipment that accepts a 0 to 5 volt signal, and provides sensitivity as well as the 10EU did, or those really old large fluorometers that we used to use. Now with the advancement of electronics comes the advancements of optics as well. So in those older model fluorometers, we used to have these bandpass broadband filters that were used, which let in all types of interference from different pigments. For example, chlorophyll being one. We would fit this filter pair that you see on the screen here into those fluorometers for looking at chlorophyll fluorescence. However, you can see that a lot of wavelengths are being detected as well. So with the advancement in optics, we are now able to choose these really narrow band filters. As a matter of fact, this filter pair that you see on the screen here is specific for looking at chlorophyll and only chlorophyll A. And it was configured with, defined by Dr. Nicholas Walshmeyer. Maybe some of you know him. He's my advisor back in grad school, but he did work in 1994 to define this wavelength pair, because we had that ability to now target specific marker pigments. And now we can do that with multiple marker pigments that we find are easy to target. For example, on the left-hand side here, you have phycocyanin, and on the right-hand side, you have phycoerythrin, and those are the excitation emission or the absorbance and fluorescence spectra for those pigments. Those are specific marker pigments that exist in cyanobacteria. Phycoerythrin can also be, can exist in higher in eukaryotic algae. But you'll notice it was difficult in the past to use broadband filters because of the spectra. And you see where the spectra overlap, where I've circled them in black there. That's a difficult thing to deal with when you're looking at optical instrumentation to pick out that fluorescence signal. Nowadays, we can pinpoint any part of that spectra, the tail end, the front end or the tail end of that curve that you see on the screen there, and then develop a fluorometer using, of course, electronics, advanced electronics, to increase the sensitivity of the fluorescence from that pigment and detect it better. And because we can do that, now we can pick out phycoerythrin-containing algae. This is Rhodomonas. It's a cryptophyte, which also contains PE. We can pick these out from mixed algal populations. We can pick out PC-containing algae mainly in freshwater environments, but in marine as well, from mixed populations. And because we can zoom in on the specific marker pigments, now we can do what? Determine the group contribution, or the percentage of that group within a mixed algal population. This is a really simple experiment I did in lab. You'll see the blue line up there is representing a green alga. The red line at the bottom is a cyanobacteria. And so I started with 2 milliliters of a green alga at the 0 mark there, and slowly, stepwise, added in cyanobacteria at those volumes on the x-axis. As I add those volumes, I'm recording the fluorescence both from chlorophyll and from PC using specialized optics. And what I'm doing is I'm using a ratio method here. So I'm ratioing PC to chlorophyll. And I'm trying to determine if my ratio reflects the percentage of cyanobacteria that is in my cuvette. And you can see at the end of the experiment here, we add almost 2 milliliters of cyanobacteria to our initial 2 milliliters of green algae. And what we get is something like 0.5. That's my ratio, around 0.5, telling me that 50% of that cuvette is cyanobacteria. And that's a great way to look at distinguishing or counting what percentage of your mixed population is this and what percentage is that. Now, we're able to take those optics, instead of having individual streams, put them into an instrument like this handheld that we released a couple of years ago called the Cyanofluor. It's actually been quite popular. And it's gaining more steam because people are figuring out that, hey, this is an easy thing to do. I don't have to go and do extractions anymore. I don't need multiple units. I can use one unit to tell me the percentage of cyanobacteria, because that's my interest. And you can see from the graph on the right here, the PC to chlorophyll ratios for cyanobacteria, which are PC-containing algae, and non-PC-containing algae, the Rhodomonas and the Tetraselmis and Dimeliella. And so these groups that don't contain PC will give you a really, really low, near 0 ratio. But the ones that do, you can see the ratio is clearly distinguishable, 4 up, and anything actually higher than 1 would indicate that cyanobacteria dominant system exists in that water sample that you've sampled. So, as I said, multiple people have purchased this instrument and are using it for that purpose. One of them is Dr. Alan Wilson from Auburn University, who has been using this religiously. And what he's doing is he's looking, because he's growing these big algal ponds, and he's doing a lot of hab research. But one of the nice features of this is, of the Cyanofluor, is that you can take the 2 streams of fluorescence values that it provides, and then use a calculator that we've put together to calculate chlorophyll pretty accurately for in vivo estimates. Where you can see on the screen here on the left-hand side is an extracted concentration of chlorophyll on the y-axis there, which he has gone through the pains of extracting and figuring out. And then it's correlated along with the Cyanofluor calculation for that chlorophyll parameter, using RFU-based, of course. And this is all on the right-hand side is in vivo-based method. On the left-hand side is in vitro. Now they compare pretty well, given that this is in vivo versus in vitro. So great correlation there, and it's quite simple by taking 2 streams of data from the unit and putting them into a spreadsheet and getting a value in less than 30 seconds, whereas the extracted would take you 24 hours plus in most cases. That only takes you so far though, right? I mean, you have algal blooms in nature, which you can't access using this type of a handheld. A handheld is you collect water from a source, put it in a cuvette, and you put it into the unit to read it. However, you have algal blooms that are offshore. You have algal blooms in areas where you can't really access every single day or be out there 24 hours. I mean, they exist anywhere. There's water. So it's tough to get at those and get good resolution for your data set using a handheld device. So what are we trying to do is go into the water. And that's the push these days that we see from people, is they're trying to go into the water versus take water out of the environment as they used to do in the old and take it back to the lab. There are all kinds of problems with doing that kind of processing. So what we have here are data from the Baltic Sea by a group that was doing sampling on a weekly basis because they were doing extractions to count those groups that you see on the left-hand side. Now, maybe that was their focus, is let's distinguish as many groups as we can using either HPLC or microscopic methods. But they're really, really limited in their resolution on a weekly basis, right? Now, between weeks 10 and 11, for example, you had a big increase in that yellow group. Did that happen overnight? Did it happen over hours? Did it happen over the matter of a week? You can't tell. All you can see is from week 10 to 11, something happened, that we had this really big blow up, and then it went away from week 13 to 14. These kinds of data can be better resolved and give us a better understanding of what's happening between those times if we were working in the environment versus taking water out of the environment to take it back to the lab. So you got to kind of ask yourself, what's more important? Do I want to understand my system more, or do I want to just take water out and see what's in there? Now, there are both thoughts, and they both could have their pros and cons, of course. But you can't really assess things like why things become decimated, coral reefs become decimated by algae. And I mean, I don't know the time scale of when this can happen, but fairly rapidly. Why food web dynamics are going to change, or the diversity that results from having a change in these dynamics. Maybe aquaculture monitoring. You can't take weekly data if you're limited to doing extractions and get a good idea for how your phytoplankton or your algae feed or stock material are maintaining over the week. So really being in the water is a lot better than taking water out. And that's the purpose of this kind of development Characterized is going to, or is working towards, is getting instruments into the water, getting people to go put instruments into the water versus our traditional benchtop take away from the environment and read. And of course, the better we become at picking out those specific marker pigments, the better we can distinguish among groups out there in real time. So we developed an instrument called the PhytoFind, which uses 3 custom sensors. These sensors are very specific. They're built with specific optical configurations for looking at specific marker pigments and trying to pick out those groups represented by that marker pigment, or that have that marker pigment, I should say. It also comes with a dissolved organic sensor. I'll talk a little bit more about that because organics are going to be the biggest killer when you go into an environment to try and do any kind of in vivo work, in situ work, especially if it's looking at chlorophyll fluorescence or any pigment fluorescence. Dissolved organics are highly interfering. So there has to be a correction for them, absolutely. And typically when people use in vivo fluorometers like chlorophyll tracking, they don't do any kind of correction using for dissolved organics. Now, turbidity isn't such a big deal, but organics are gonna really affect your signal. So the sensor here does an automatic correction to remove that interference from the signal. And of course, has standard depth, wiper, standard probe, temp probe, and then 600 meter deployment, those sorts of things. But what you end up with is a nice trace for in vivo calculated or in vivo fluorescence based estimates. Now this is in the closed circles you see there. Each color has a closed circle and an open circle. The closed is going to be extractions we've done in the lab for that culture. And the open circles are what the PhytoFind is estimating that culture as. You're going to see differences, you're going to see variability, but the trend, the trace is the same. It tracks very well over time and over culture. So you can use this type of system for monitoring freshwater marine environments. They're used in Fairybox installations for flow through. There's surveying, HAB tracking. They can be used in towed, moored, or profiling mode. What's nice is that they're factory calibrated. Most sensors these days are not, but the PhytoFind is factory calibrated, and that's kind of the advanced nature we're working towards, is calibrating our instruments so that it takes the burden off of customers, because there's a lot of issues out there that we find with people trying to find calibration standards for fluorometers, and it's a difficult thing to do. So we've calibrated our PhytoFind, and the reason for that is because our wavelengths are very specific, and we have very specific calibration solutions to use. And we've determined interferences, the biggest interferences, and we're corrected for them, which is dissolved organics. And then we've developed some kind of an algorithm that takes all of that and puts it into, and then gives you a nice estimate. And I'll get to that in a little bit, but before I get there, I want to say, as with every instrument that you're going to put into the water, you're going to need, your ammo. And it's to fight biofouling, like the copper wiper arms, or to maintain or to check stability of the sensor using a solid standard cap. Maybe you want to do depth profiling. Well, with depth profiling, you're going to need to transfer a signal long distance, and to do that, you have to convert it to 422. So we have digital converters. We have copper plates, shade caps, things like that, high cap batteries. And then with that, we also provide software, and it's actually intuitive software, which allows you to plot your group percentages, see them in real time. You get detailed graphs. You also get actual values as percentage of that group within the total, and then the microgram per liter concentration of that group within the total. And what's nice, you see that total chlorophyll microgram per liter concentration of chlorophyll. It's more accurate than the Cyanofluor one. The Cyanofluor, if you remember, used 2 channels. Now this one uses 3 sensors. So the more sensors you put into calculating the total chlorophyll, the more accurate your chlorophyll estimate is. And this is using in vivo fluorescence again. So how do we go about the calibration? And this is just an example. This isn't the exact one. But we use representatives from each group we're trying to target. Rhodomonas, for example, PE containing. Cyanobacteria, PC containing. Dinolala, neither one of those. It's a green alga. And each group or each representative is going to be seen differently by the 3 different sensors. That's the plot you're seeing there. There are 3 cal curves, I guess we'll call them, for each alga, and each one has 3 coefficients, and you'll see the coefficients, and that's the coefficient or the slope per sensor, and they differ. And we can use those in combination with how each sensor responds to dissolved organics and do some corrections and stick it in our nice small equation. Don't copy this, this is just an example. And we come up with something that gives you a really good estimate. So for example, and let me orient you here a little bit because it seems a little busy. We're looking at 20 microgram per liter of chlorophyll in that ratio of algae, which you see green done is 76% of that, contributing to the 20 microgram per liter. 14% is the mixed PE containing. Cyanobacteria are 10% of that mixed population, but the population total has 20 microgram per liter of chlorophyll via extraction. We added to it 40 milligram per liter of dissolved organics. And what you see on the right-hand side is an uncorrected response from the PhytoFind showing you 72%, or telling you that 72% of the population is actually the mixed group, and the mixed group is the red, okay? We know that not to be the case. But what is that? And that's how badly dissolved organics can skew our data or give us errors, okay? But our corrected values on the left-hand side there bring us back to our normal state, which is what our expected state of 76, 14, and 10. And we see it's 73, 17, and 10. Of course, expect some variability. That's just what happens within vivo studies. But you'll see how important it is to correct for dissolved organics, and the PhytoFind actually does it on the fly. And we've done several, and this is only a few examples of, and this is just 2 PhytoFinds paired together, calibrated at different times. And their responses are pretty close to one another. They're not completely off. And we've done, here, let me go on next one. And then this is just some data from a deployment that we did not too long ago, and it was on the order of maybe, what, a week or two. And, you know, put the PhytoFind in at a location in the San Francisco Bay, and then tracked to see any changes. And we could, you know, very nicely see the tidal changes and how they affected the contribution of each group at that time. So you can get, it's almost like a one-stop shop with this instrument, but I mean, I'm sure there are other parameters you could be measuring, you would like to measure, but you can get really nice, robust, very, very highly resolved data sets on the order of per second. And the PhytoFind has also been compared during beta testing with another fluorometer that you guys may be familiar with, is a BBE fluoroprobe. And we did side-by-side using our beta testers to see how well we compared. And the comparison actually pretty good, given that the BBE has a lot more bells and whistles. It has, if I'm not mistaken, 5 to 6 channels. They're just a lot higher. So the PhytoFind would be like the, you know, the BBE's little brother or something like that. But the comparison in what we're trying to distinguish, which are those algal groups, turned out to be very nice comparison with the BBE, which is, again, limited availability of this type of instrumentation on the market. And we are one of the, I believe, 3 that exist. There may be more, I may be wrong. So what it comes down to is variability in the field. This was one of the questions that was asked. Expect a high degree of variability, not any higher than what you already get from your in vivo studies, your in situ studies. These types of systems were great for predicting onset of blooms because you're monitoring continuously for that signal. And they estimate chlorophyll very well because you're using multiple wavelengths, multiple specific wavelengths to account for all the different groups that make up this mixed population, this matrix of algae. So you can distinguish among the groups, and you can calculate the chlorophyll very nicely, and it's got some great correlation for dissolved organics, which is a huge source of interference for any in vivo or in situ measurement that you're making in the field. I believe that was the end of our talk. We're open to questions. It was a very quick talk, and I think I answered some of the questions. I can read through the questions if Vanessa or Douglas, you guys want to give me the okay to read through the questions and go through and answer them?
Yeah, go right ahead.
Okay, so one of the questions that came in, has this technology been used to determine algal pond infection? No, it has not, but it can detect changes in, and it doesn't really detect the health of algae. That was one of the questions asked, does it detect the health of algae? But health is more related to active fluorescence. We're talking about specific fluorescence, similar to bulk fluorescence. So we don't do anything with health, but it can detect changes in algal groups on the order of seconds, per second, sorry, is the fastest sampling rate. The second question, can you differentiate between diatoms and dinoflagellates? Unfortunately not. Diatoms and dinoflagellates have the same makeup other than carotenoid. The carotenoid is different. Diatoms have peridinin, dinoflagellates have fucoxanthin. On the basis of those 2 carotenoids, yes, we can, not with fluorescence, because carotenoids aren't fluorescent. So we'd have to use a different way of distinguishing among those groups. Third question, how well does the system handle bubbles or disturbances in water? About as well as any other system that does. So if you have instruments that are in the water that are looking at in vivo type fluorescence and bubbles are a big disturbance, it's going to be the same thing. It's pretty much what people are already doing who are working in situ, with in situ instruments. You get the same effect. So there's not any better effect. That's just what it is when you're working in natural waters. Max depth rating of the fluorometer, 600 meters. Device calibration and qualitative data over time. Yes, so the device is calibrated at the factory before it's sent. So there's no calibration necessary. We do provide those solid standards for checking stability of the instrument over time. It's a very nice check. The solid standards don't degrade, they don't change. So you set them to some concentration and then you just monitor that over time, pull the unit out, pop the standard on, and see if it's maintained. Can you describe the optical?
Can I ask?
Yeah.
Yeah, I was just going to ask a question about how often does the instrument need to be recalibrated, or is that, what's the long-term drift capability of the sensor?
So with solid state instruments, there is no drift. These things don't drift because they're LED driven and they're very, very low power. Okay, so you don't have a fading lamp. You don't have filters being burned through. You don't have any polarizers. It's pretty much electronics, LED photodiode, glass filters. So there really isn't drift. There's more drift in the sense of things growing on the optical head. Maybe there's, if you're keeping it clean, maintaining it, there should be no change in the signal. For years, LEDs, I think, are rated for 11 years for the visible wavelengths, and these are all being used. All the ones being used here are visible. So they're driven low power. So that's why there's no drift in the system. But we offer the calibration, the solid standards for checking signal, just for peace of mind. Some people don't believe us. Hard to believe us. But yeah, for peace of mind, you buy it, you pop it on there, and you can tell that, this thing is maintained. And there are times when it will fail maybe, and the solid center will catch that as well. But for the most part, if everything remains the same, as far as electronics and optics not, then it will be stable. There was, let's see, can I describe optoelectronics that allow you to make the measurements? Yes, I can say they're LED and photodiode and glass filter. I can't tell you what wavelengths they are, unfortunately. That is proprietary information. If we told you, everyone can go and replicate their own FlytoFind, we will. I kind of don't want to stay away from that. How does this technology deal with increased noise with extremely dense blooms? Good question, a tough one to answer. I don't exactly know. The max, I can tell you the max concentration of the instrument is 100 microgram per liter. Blooms typically, maybe about 60 to 90 microgram per liter. So at those levels, I don't think noise is an issue. It's not like the noise would increase to a level near the signal. For example, if you have 30,000 relative fluorescence units, that's just fluorescence units that you're reading, your noise isn't going to jump up to 20,000 standard deviation, in that data set that you're taking. It's going to stay really low. So the higher the signal, even though the noise jumps up slightly because of the density of the bloom, it's not going to come near the signal that you're getting. So the signal to noise stays pretty far, pretty big. But again, a tough one to answer. I can't give you numbers on that. It's just one of those things you have to experience, I think. Open to any other questions. Those were all the questions that were on my list here. And Phil says, let's see, your data been compared with satellite chlorophyll? No. So again, Phil, it's one of the newer units. It was released last year. We've had a couple of sales, and those sales are more probing to see how well the instrument works. I can tell you that we've had great feedback from this group. It's one of the higher end groups that has purchased the instrument. I can't tell you who it is. They're trying to keep us hush hush right now, but great feedback from them in the qualification period that they have, because people don't instantly jump into a sensor that costs 20, 25K. You have to see what, and these are the kinds of questions that you guys you guys are going to ask. How did it perform here? How did it perform there? And because it was released last year and people are still in that qualification state, we really don't have those answers. But as the more we get the case studies in, and we're allowed to share them, we would put them on our website for everyone to see. So it's not something we're trying to hide here. Unfortunately, we missed the qualification. I believe ACT did a qualification on something like this, similar. And this unit was released after that had happened. But if you guys know of Alliance for Coastal Technologies, they do qualifications like this every once in a while, or evaluations, we'll call them. And the next one that comes about, if it has anything related to this instrument, we're definitely going to be on board. We actually have all of our instruments. Anytime they say, oh, we have an evaluation coming up, we offer up our instruments because we know that they work well in the environment. couple of other, I'm going to open up the chat because I don't have it open for some reason. Okay. That's all I have actually from Phil.
Yeah, I had a question, just like the power requirement. You mentioned you're using LEDs, which are low power, but overall, what's the system draw?
The system draw, I'd have to look it up. I don't have it. It is on our website, on our data sheet. We have all of our power specs online.
Sure.
I believe it's 300 milliwatt, but I'm not sure. You'd have to check online to see if that's the case. We have a high cap battery, which can last for, I want to say 3 months, and that's 6,600 milliamp hour, drawing, let's see, every 10-minute sampling. So if it's a quick cal you can do in your hand, that's great, but I believe it's 300 milliwatt. Again, I urge you guys to go to our website, characterizing.com, open up PhytoFind, open up the product data sheet. All the specs are there for anything that you need.
Actually, I've got some power draw figures for you. So
Pat can look all those up right away.
So right now I'm looking it up. Maximum current draw at 12 volts in operational mode is at 300 milliamps, and in sleep mode it's 3 milliamps.
There you go. Okay.
And then the DC power required is 8 to 30 volts, 2.2 amps.
So
okay. And then is there a, yeah, that is. And is there a, like a planning spreadsheet or something like that, so you can figure out based upon a sample rate and how often the wiper is running?
Yes.
And just the parameters for figuring that out, so you don't have to calculate that yourself.
Right. We do have a battery calculator online. And this battery calculator pretty much says, hey, you know, put in your wiping interval, put in how many sensors you have, and it calculates for you how long you have to deploy based on those inputs that you put in there for the battery that you have. So using that, and we're very conservative on that. So if we say 24 days, you could go probably 32 days and you'd be fine. But we try and cut you off and say, this is how long you have, just to make sure you don't run out of battery power and you collect all the data you need to collect within that time.
Great. All right, well, I think that finishes all our questions. Really appreciate you guys coming out today, and it looks like a really interesting instrument. And the rest of the group out there, you know, we're always looking to bring additional speakers. So if you have some company or some technology you'd like us to have featured here on the Scripps Technical Forum, please don't hesitate to reach out to us, and we'll put it up there. And then if you missed the beginning of this for any reason and came in late, just go to the Scripps, the stf.ucsd.edu website, and we'll find a link in a few days for the full webinar. All right. Well, thank you, everyone. Have a good weekend.
Appreciate it. Everyone have a good weekend.
Thanks.